Suppose that we have three data distributions A, B, and C that looks like this. Are there any similarities or differences between them? Well, all three curves have symmetrical bell shape. If we were to calculate the measure of central tendency, we are likely to find that all three curves have roughly the same mean. Nevertheless, our eyes tells us that the three curves are definitely not the same. Curve A is taller and stays closer to the mean. Curve B is a little shorter and wider, and curve C is the shortest but the widest. This indicates that the data are spread out differently. How far is each data value from the mean? How scattered are the data? The descriptive measure of such dispersion can provide valuable info as well. In this section, we'll focus on the descriptive measure of dispersion. It is really about finding the numbers that indicate how scattered the data are. Some measures of dispersion we will learn are the range, interquartile range, variance, standard deviation, and coefficient of variations. The range is the simplest measure of dispersion, where we find the difference between the largest and the smallest data values. Regardless of whether we are dealing with population or sample, the definition of range remains unchanged for discrete data. Although it is easy to use and simple to understand, the problem with it is that it recognizes only the extreme values of the data and may give a distorted representation. In this example, we are given this data array. To find a range, simply pick up the largest value, which is 93, and minus out the smallest value, which is 52, to get the range as 41. We have seen earlier that median is the data value that occupies the middle position, and it divides the data into two equal parts. Quartile works on the same principle, but divides the data into four equal parts instead. The first quartile, or Q sub 1, is the number where 25% of the data points fall below Q sub 1. The second quartile, or Q sub 2, is the number where 50% of the data points fall below Q sub 2. The third quartile, or Q sub 3, is the number where 75% of the data points fall below Q sub 3. Since the second quartile is the number where 50% of the data falls below it, that's exactly the same as median, which we have encountered earlier. The alternative name for the first quartile is the lower quartile, and the alternative name for the third quartile is the upper quartile. Given a set of discrete data array, Q sub 1 is the 1 over 4 times bracket n plus 1 value. Q sub 2 is the 2 over 4 times bracket n plus 1 value. Q sub 3 is the 3 over 4 times bracket n plus 1 value. If dealing with population, then the population size capital N is used. If dealing with sample, then the sample size small n is used. The reason for learning about quartiles is so that we can use them for these two descriptors. Interquartile range, or IQR, is the difference between Q sub 3 and Q sub 1. The quartile deviation, or semi-quartile range, simply means to take the interquartile range and divide it by 2. Regardless of whether it is a population or a sample, the formula remains unchanged. The beauty about these two descriptors is that they reduce the importance of extreme values. Unlike the range, which only consider extreme values, these two descriptors make more complete use of the whole data set. Hence, they are more meaningful than the range. In this example, we are to find the quartiles, interquartile range, and quartile deviation. To get the first, second, and third quartiles, here are the formulas. Since n is equal to 20 in this case, substitute into the formulas to get the appropriate position of the data. For Q sub 1, prorate between the 5th and 6th value to get 61.5. For Q sub 2, take the average of the 10th and the 11th value to get 68.5. For Q sub 3, prorate between the 15th and the 16th value to get 78.5. To find the interquartile range, take Q sub 3 minus Q sub 1 to get 17. To get the quartile deviation, take the interquartile range and divide by 2 to get 8.5. We'll now use a box plot to visually represent the range, quartiles, and interquartile range. To do that, start by plotting the minimum and maximum values, and the first, second, and third quartiles on a number line like this. Next, draw a box stretching from Q sub 1 to Q sub 3 like this. Finally, divide the box into 2 at Q sub 2 like this. That completes the picture and helps us to bring all the measures and descriptors together. Applying it to our earlier example, where the minimum, maximum, and all the quartiles have been found, let's draw the box plot. Start by plotting the minimum and maximum values, and the first, second, and third quartiles on a number line like this. Next, draw a box stretching from Q sub 1 to Q sub 3 like this. Finally, divide the box into 2 at Q sub 2 like this. And there you have it.